Our society is being confronted by unexpected outcomes, unexpected events, or challenges with increasing frequency and intensity. I say here whether in the form of natural disasters, cyber attack, financial shocks, and I added this morning, election outcomes. Recent events have largely been unpredictable. There's been changes in dynamics, both natural and social, that make everything difficult to anticipate. Yet our ability to thrive in the coming century depends strongly on our capacity to anticipate these kinds of events or these risks, and even if we can't avoid them, absorb them or adapt to them. While risk assessment as a practice has a rich history in the fields of engineering, the conventional methods tend to have some assumptions that don't hold so much in today's world. They tend to assume well-characterized risks that are described by standard probability distributions that are stable over time. And yet, again, as I say, these don't tend to hold for contemporary risks where situations are often without precedent and conditions are continually changing. So for these reasons, research progress is needed in areas of developing technologies, practices, policies that can demonstrate resilience by being able to perform in unexpected situations or dynamically alter their behavior and effectively adapt to change. And so what I'll be talking about today, this concept of resilience as a counter to, as a measure of means for addressing risks, in using the tools of decision theory. And I'll be on climate change assessment as an example, although I'll address how this can apply to other types of situations. And I'll start with the Bayesian approach because I recognize that all of you will have had training in decision theory. It's actually not something that's a part of much of the university curriculum or even engineering curriculum. I'll talk about the methodological advancements that have been made recently, including by our research group, and challenges moving forward, what kind of opportunities or challenges there are. And then I'll draw this connection back more explicitly to the issue of resilience, which I think has the potential to be a theme among a lot of the work that's here at Pratt. And I'll summarize, as I mentioned, with some other projects that exemplify other types of application areas for this method. So this is a simplified decision tree for climate change decisions, how we handle climate, what kind of climate policies we might pursue as a country or as a world. Just very simply, imagine if we had two options: reduce emissions in the effort to try to combat change, or we could decide to do nothing. In part, will depend upon some factors for which we're not entirely certain. One of the key ones is the sensitivity of the climate. That is to say, how much does the climate, let's say broadly characterized by global average temperature, respond to the greenhouse gases that are being emitted into the atmosphere? The response could either be quite strong or it could be quite weak, and there could be a bit of debate numerically. The outcome, in any case, the end point of this decision tree would depend upon both our decision and this uncertain event. And so just to characterize these by some layman's terms, we could think of, if we reduce emissions, it turns out that the climate strongly responds to those emissions, then we could imagine calling this a scenario an averted catastrophe. That is, we had the potential to really have a problem, but we managed to head it off by reducing our emissions sufficiently. If, on the other hand, the climate is weakly sensitive, then we would have reduced the emissions unnecessarily. And so this is the kind of counter argument to why we shouldn't reduce emissions. Just because if we were to do it and it turns out that the climate doesn't really respond in the way we think it might, we would have gone through all that unnecessarily. On the other hand, if we do nothing and it turns out that there's a strong response, then we would have not acted in the face of this potential catastrophe. Or if we do nothing and it turns out to be weak, well, then we got lucky, right? That we didn't do anything, but we also didn't spend money unnecessarily. And while these numbers aren't meant to be numerically accurate, let's just put some numbers on it. Again, thinking of the catastrophic outcome as being the absolute worst, getting lucky as being the best in the sense of neither spending money nor having damages, and these two both being somewhere in between. You can see it's a classic example of a kind of risky decision. Doing nothing has both the best and the worst outcomes, while doing this has intermediate outcomes. Now, how would we decide among these? Well, traditionally in the decision theoretic literature, you take the expected value of the outcomes. expected value, meaning the probability-weighted expectation, probability-weighted average of the outcomes. So we need probabilities. And again, these aren't meant right now to be representative of anything, but let's say there's a 30% chance that we could characterize this climate response as strong, and a 70% chance that it would be weak. Well, whether we reduce emissions or not doesn't change those probabilities. It just changes the outcomes given the decision and the status of climate sensitivity. So we have the same probabilities down here. And so a probability-weighted average would simply be the expected cost, the probability times the corresponding cost, summed up for these two possibilities. And so in this case, it would be 0.3 times 0.5, 0.7 times 1, or 0.85 trillion. And down here, the same math would give 0.6 trillion. And since these are costs, we want to minimize the cost. And so we would choose to do nothing in this scenario, given this situation, given the balance of probabilities and outcomes. I'd forgotten I was going to dim the lights a little bit. Is anybody having trouble seeing the details of the screen? Oh, please, mine. Okay. The true reality of the situation is that making decisions based upon simply expected costs isn't a reasonable way to go descriptively, because in reality, society is actually not indifferent to the components of risk, which aren't captured in that. Most of us, it turns out, are risk averse, that we make decisions such as buying insurance because we want to avoid a catastrophic outcome like our house burning down, or avoid the expense associated with that. So we're willing to pay something on a regular basis to buffer that kind of a risk. So risk averse in this decision theoretic framework can be described by a concave utility function. Here's one functional form, again, as a function of cost, and a parameter gamma that characterizes the degree of risk aversion. This is just a function called a utility function over whatever variable we might be assessing the outcome on, in this case, costs of climate change in trillions. And the reason why this captures risk aversion is because imagine, I wanted to use a 50-50 gamble here rather than the 30-70 that I showed earlier, just to make the math easier. Imagine we had a 50-50 chance of this outcome or this outcome, right? And now we took the utilities associated with those, so the utility of 0 and the utility of -2. If we took now the 50-50 gamble, the expected utility of these numbers, that would be the average of the two, and we run that back through the inverse of the utility function, the dollar value we get turns out to be numerically less than the expected value of these two. And that's a property of a concave function. It's referred to as Jensen's inequality, that the value associated with the expected outcome is going to be less than the expected outcome itself. And the difference between those is referred to as the risk premium. It's effectively how much we would be willing to give up, given this particular degree of risk aversion, in order to avoid the risky proposition here of potentially losing $2 trillion. And now, again, if we're going to use this shape as a utility function, we could just pop it right into this expression. And again, this gamma reflects the strength of risk aversion, so that our decisions in such circumstances are keenly dependent upon the strength of risk aversion, but higher values of gamma meaning steeper shapes of the utility function. So turning back to our kind of caricature here, if we were to then use a utility function of the form I just described with a value of gamma value 2, which is something that people kind of throw around as a reasonable representation maybe of risk aversion, I plugged in the numbers here. These are what you get. So now if you take the expected utility of each of these, again, same probabilities, but now using utility instead of cost, you plug in the numbers and you get 0.9 here and 0.7. And because higher utility is better than lower utility as an expression of our preferences, then now we would choose to reduce emissions. And again, because we're risk averse, we can see that that's consistent with the fact that this is the riskier outcome. And while on average it may be more desirable monetarily, when we consider risk aversion, this becomes more desirable. Now, if we turn back to a more realistic framing of the climate change problem, I think we can say at this point with confidence that we know that climate change will have costs. It will lead to loss of biodiversity and ecosystem services. It will lead to sea level rise and associated loss of life and property, things like desertification, water shortages, changes in agricultural productivity, impacts on human health. And on the counterbalancing side, if we were to try to avoid these, we would have costs associated with abating those emissions and adapting or avoidance measures to these kinds of changes. And so there'll be costs one way or the other given where we are in today's world. So the problem is often framed in a quantitative modeling sense as a kind of trade-off between known damage and abatement costs. And with a little bit more of a realistic caricature now here, if a weak emissions reduction, meaning not doing much, essentially allows damages to grow in the future without having to spend much, simultaneously not spending much in the way of abatement costs. Whereas if we were to take strong emissions reductions, we would have high abatement costs in the near term, but that would be counterbalanced by a supposed reduction in future damages. Now, the risk of extremes has largely been overlooked in these kinds of analyses. And there are potential extremes, kinds of black swans, not unlike what we saw yesterday, things that could happen that could actually very much change relative to the expected outcome. So things like sudden changes and sudden losses of Arctic and Antarctic sea ice, disruptions of major circulation patterns or changes in monsoons, feedbacks in the case of forest dieback, so other socioeconomic terms like dramatic changes in population perhaps as a result of increases in lifetimes or changes in lifetimes, and changes in global economic conditions that may not currently be anticipated. And so if we superimpose a kind of shaded area here representing the uncertainties introduced by some of these, that presents the risk in a probabilistic sense that isn't captured by the solid lines. And if you look at something like this, it's a relatively high risk situation, and this is a relatively more moderate risk situation, similar to what I showed in the caricature decision tree a minute ago. So we undertook a project to try to follow through on this concept in a numerically rigorous way. And we did that by first developing a fully probabilistic model of climate change that had previous models that tried to capture uncertainty hadn't captured many of the same factors that we addressed. We tried to get a better assessment of what is the true descriptive aversion to risk of society based on some available empirical data, and then put this together to perform a decision theoretic analysis of what this would mean for what would be the kind of socially optimal CO2 emissions reductions. And our speculation going into this was that with high uncertainty and potentially a more realistic risk attitudes, the risk reduction value of emissions abatement may be large, and in fact may be numerically larger than simply the expected reduction in damages that might be incurred by emissions abatement. In other words, the insurance value might be more valuable than the actual anticipated reduction in damages itself. So I'm not going to get into the details today, but we developed a climate model based upon an available integrated assessment model called DICE. And of course, in any kind of modeling, there's uncertainties, particularly in climate change forecasting. These kinds of integrated assessment models take inputs, and some of the key ones in most models are population growth, economic growth, and the specific emission scenarios, which you can think of as a kind of carbon intensity of the economy. Those get plugged into models of the energy, economic, and geophysical system and the feedbacks between those. And then the outputs of most of these are in economic terms, something like consumption per capita, which you could think of as something like GDP. And so we focused on uncertainty in 7 key parameters. We addressed uncertainty in the future population growth rate, in total factor productivity, that is how efficiently the economy uses resources, the change in carbon intensity of the economy, this climate sensitivity factor I mentioned earlier, and carbon cycle mass transfer coefficients, that is how carbon changes among the various pools around the globe. And then also uncertainties in what would be the damages associated with a given level of climate change, and uncertainties in the abatement costs, which again, they are also uncertain themselves, as you saw in the blue shaded area in the previous figure. And so this is, and then I meant to mention here, and then emissions weren't reflected by uncertainty. Those are the control parameter that we have in this situation. And so we looked at how would the outputs in the case of economic consumption per capita change as a function of different emission scenarios. And then ultimately what we're interested in is converting this through a characterization of risk attitudes to utility as opposed to just consumption. So here's a representation of some of the key model components for one scenario, the business as usual emissions scenario. The black line being the median prediction, and the shaded area being the 90th predictive interval, which you may have a hard time seeing. But here we have emissions, which this is over the next 200 years, has quite a bit of uncertainty associated with it, going from here to here by 2200 as a result of the various parameters I showed earlier in model inputs. Here's anticipated average temperature change. Here are the damages, again, quite uncertain, coming from climate change, and then the impact, or the implication for consumption per capita. So these are all uncertain. As I mentioned, we then take this and we want to convert this to present value expected utility as the actual metric of human welfare as opposed to just the economic metric. And so we need a characterization of the risk attitude, and we need time discounting, because these are changing over time. And in any kind of analysis like this that has a long time horizon, you want to use a discounting rate that reflects time preferences. So how did we come up with these? Well, some studies that were in the social sciences literature had done surveys of how people responded in their own personal decisions, or how they felt society in general should respond to risky situations. Some of the more well-known ones of larger sample sizes, one asked a survey regarding personal financial decisions, and based on the answers to those decisions was able to back out a value for this gamma parameter, and estimated it to be values of greater than 3.75 in this case. Again, remember I mentioned 2 as kind of being a reference point for many studies. Questions regarding economic impacts of national policy measures and people's preferences for those also reflected similarly high values for this key parameter. We decided not to rely upon those social scientific studies or the survey-based studies, but rather to use a statistical database approach to try to infer what would be the value of this that would be consistent with investment behavior around the world as reflected in the financial markets. And so there are investments that have different levels of risk. You could think of stocks as being relatively risky investments and bonds as being relatively safe. And when we try to look at the difference in return between those in the context of any particular country's general economic growth, we can infer something about what the risk attitude is of investors in that country. And so we gathered use data that were available, I should say, on annual consumption growth, that being one of the key components that we're using as a measure of outcome in our climate model. And so we take this to be a reasonable economic metric and to reflect risk attitudes towards economic changes. And then data on returns on stocks and bonds from 24 nations over the last 100 plus years. And we did something called a Bayesian hierarchical analysis. And if any of you have studied statistics, modern statistics in a Bayesian context, the Bayesian approach is distinctive in the sense that in this context, it gives each nation its own particular parameter values, but assumes some commonality among all the nations with respect to a kind of a global distribution. And the purpose behind this is it allows for greater power in your statistical estimation. Rather than only relying upon any one country, you can kind of pool the data, but not necessarily assume that all the countries, in this case, all the replicates, are identical to one another. One of the interesting things that's relevant to what I mentioned earlier is that in these data, one of the key components is the context of the country's economic growth. And so we looked at year over year consumption growth as a measure of that. And when we went to fit distributions to the long-term 100-plus historical record of these countries, while many economic modelers had used a symmetric probability distribution, it turns out that the data are highly indicative of fat lower tail, meaning that disastrous years, years in which there's negative economic growth, are much more common than would be expected by a symmetric distribution. This is a kind of black swan effect that some of you may have heard about, where conventional kind of symmetric distributions that tend to be so-called thin-tailed tend to underestimate disastrous events, or extreme events, I should say. And so we think that we did a better job of capturing that by developing a more distinctive probability of distribution that uses a power law over the central components of the distribution. I'm sorry, power law over the tail components of the distribution that allows for this kind of fatter tail, a greater probability, greater likelihood over for negative growth years. And so again, in the fit, we allowed each country to have its own distribution, and there was uncertainty about that itself. And so these are some of the distributions reflecting the data from the different countries. You see some are narrower, some are wider, and you can't quite see it, I imagine, but there's gray shading around these that indicates the uncertainty in that. Now, from that, together with the stocks and treasury bills, actually, data that are considered the safe versus the risky investments, we could estimate, and the difference between those being the risk premium, we could estimate this value of gamma. And we did this for each of the countries using this Bayesian hierarchical method. And so along the vertical axis these are called bean plots. This is a kind of distribution reflecting the uncertainty in the estimate for a given country. And the key point to take away here is not so much the country-to-country differences, but the overall average of being 5.6 in the ballpark of what I showed you for the social scientific surveys. And so now what are the implications of this kind of level of risk aversion, stronger than we might typically think, for optimal emissions reduction? So we can now use this value of gamma, and we chose a time discounting rate that's relatively well accepted in the climate modeling literature of 1.5% per year. And what I want to remind you of is this isn't just used for post hoc processing of the results, but rather it's used as a reflection of the decision criteria of the individual actors within the model. And so the fact that this is the case, that they were responding in a strongly risk-averse way to fat-tailed distributions, added some computational complexity here, where we really needed large numbers of samples to make sure we were getting those lower tails, which tend to drive the situation in this case. So what does this mean then? Well, here's a characterization of relative utility, where higher values are more desirable, versus the level of emissions reduction by 2050. And so we have these kinds of S-curves that we assumed for the different emissions reductions policies. And as an indicator of the rate of change over the next 100 years, we use the value at 2050. Just not that we would only implement that at 2050, but that would be a reflection of the pace that we were going at that point. And so if we go from 0 to near 100 here, and we use the value of gamma equals 2, that argues for relatively modest emissions reductions on the order of 25% or so as being optimal. And that the drop-off in utility but towards higher values means that the risk of over abating is greater than the risk of under abating, meaning of spending too much. This drops off more steeply. On the other hand, if we use the empirically supported value of 5.6, then we see the opposite effect, where under abating is much more risky than over abating, which is probably consistent with most of our intuition as scientists, is that doing nothing about climate change is likely to be riskier than doing too much. And the optimal level is much more aggressive in being closer to 40 or 50% reduction by 2050. And if we look back now at the distribution of impacts, this is just indicating the probability of severe impacts as indicated by a catastrophe. That's a significant loss in overall economic consumption. You can see that this sharp drop-off is reflective of an increase in the probability of catastrophe as we do less and less, moving to the left. And so the conclusion here is that strong risk aversion tends to put greater weight on protection against the most severe outcomes. Okay, and so turning back here, that's the conclusion of that particular piece, kind of a description of risk attitudes and a characterization of distributions associated with uncertainty associated with climate change. I want to turn back to this kind of caricature to point out another challenge that we faced in this endeavor, and that climate modelers in general face, is how do we actually go about assessing the distributions that we use in this model? Back when I said we had uncertain characterizations of some of the key components, I didn't tell you what we actually chose for those other than the consumption distribution. This uncertain component here, whether it be climate sensitivity or anything else that drives differences in the social costs, is generally based on a model-based assessment. And the state of the art in model-based assessment is Bayesian risk assessment. Bayesian's analysis, for those of you who aren't familiar, is essentially a procedure that requires one to begin by stating your knowledge about a particular uncertain quantity, and then what it does is stipulates the way in which that knowledge can be updated as you gain new information. So it starts with something called a prior distribution. Again, it's reflective of your your current knowledge in the form of a probability distribution, which is subjective, meaning it's a measure of your own relative degree of belief. It's not something that's observable in the real world, but it's a measure of your degree of belief. And it can be scientific degree of belief or pooled degrees of belief, but it's a subjective assessment. And then Bayes' theorem, or Bayes' rule, is used to update this knowledge as more evidence becomes available. This is particularly relevant in something like climate change. And in fact, turning back to the election example, it's relevant in something like that, where you're getting new poll information, new data as you go, and you want to incorporate that, not necessarily ignoring everything you believed to that point. And so as we have data from the past and moving into the future on things like global average temperature, then Bayesian updating is a natural way to incorporate the learning from that information, or the key model parameters in these kinds of decision supporting models. So I'm going to introduce a little bit of notation before getting into some of the details here. We have model predictions, and my notation is that that's going to be a function, y sub m, which is a function of inputs and parameters characterized in general by theta. That's a vector of inputs and parameters. Under the Bayesian context, we use probability distributions to describe the knowledge, or degree of knowledge about these parameters, as I described a moment ago. And we start out with some prior knowledge, so probability distribution about these parameters. And again, it's not just one, it's whatever components of the system we might be uncertain about. We can gather data as we go, y measured. Those are measurements of what the model is predicting. And a key component is what's the likelihood function of those measurements? In other words, how likely is it to observe the particular set of data we observe, or could imagine observing, given particular values of the parameters? This is a kind of, you can think of this as the distribution of the model errors. And so what Bayes' theorem says then is we can update our parameters given some measurements simply by multiplying our prior distribution times our likelihood distribution and dividing it by what's essentially a constant, which is the integral of that product over all values of theta. And so because this is a constant, you often see this written as the posterior distribution is simply proportional to the prior times the likelihood. And no matter how simple or complex a model, this principle can hold. There's just some numerical complexity involved when you have more complex models. And so what I want to get into is a little bit of some of that complexity, because I think it's brushed under the rug a bit when you read about some climate-based, model-based assessments of climate change. One of the key ones is, what is the likelihood function in such a model? Most statistical textbooks, including Bayesian ones, would tell you, well, it may not be unreasonable to assume that you have measurement error. That is, where your measurements, the data you observe, might be centered around some model predictions, but they have some error associated with them, epsilon here. So you have a dynamic model, which is a function of time and model parameters, and then some random noise component here, which is your model error. The model error is just simply characterized as the difference between the data and the model. So it would be the vertical difference between the points and the line here. And oftentimes, we assume that that's normally distributed with mean zero and the fixed variance. That our measurement noise is centered on our model predictions, and there's some variance associated with it. And even this is a result of one of the more advanced climate models, and you see, that kind of assumption obviously doesn't hold, right? We don't have IID that is independently and identically distributed errors around some central point. There's strong autocorrelation here, strong departures that depart from that. And so we can't just necessarily assume a normal Gaussian likelihood function. Some people have tried to address this by introducing a time-dependent error term, basically saying is that we can have some component here that's not just a random noise term, but actually has some systematic function with time, like a smoothing function. The problem with that is, as you might anticipate, this violates the basic assumptions of the model, like heat bands. If you just introduce some systematic component that's not random, then, and that temperature is just going to depart from this, well, where is that heat coming from, right? And if we're going to violate one of the basic thermodynamic principles of climate modeling, then what's the basis in developing a kind of process-based, descriptive, physically-based model? So an idea we had was, what if instead of making the error terms time-dependent, let's make some of the parameters themselves time-dependent. that would typically then allow the model to adhere to the basic thermodynamic or mass balance assumptions, and yet may give us some ability to better model data. And so we could then estimate the time-dependent structure of these uncertain parameters from available data. So this is kind of like a continuous time Kalman filter for those of you who are electrical engineers. So one of the key components here that's strongly time-dependent and yet prone to error is historical reconstructions of climate forcing. These are generally coming from historical records, whether they be ice core records or they be any other measure of looking at what the forcing, that is the climate change forcing, has been historically. And these errors could very well have a time-dependent structure because they might have some systematic components that have been misestimated historically. So our premise was we could estimate a time-dependent deviation between the inferred forcing from the model and the historic reconstructions coming from the data. So that would be this component here, that essentially is a reconstructed forcing plus some time-dependent component. And then now we needed to constrain this a bit, and so we used the stochastic mean reverting Ornstein-Uhlenbeck process, which you might be familiar with. Again, I think it's probably more used by electrical engineers than civil and environmental engineers. And those of you that are familiar with it will see the specifics here. Basically, what we're characterizing is, well, some parameters of the model, which aren't time-dependent, and we estimated those using a Markov chain Monte Carlo algorithm, which is the state-of-the-art for Bayesian inference. And then we have parameters of this Ornstein-Uhlenbeck process, tau, the characteristic time component, and sigma, the variance. And these couldn't be included in the MCMC algorithm because it basically, the MCMC algorithm wouldn't converge to these many dimensions of uncertainty, but we could use a cross-validation technique that we developed in order to select these parameters while in an iterative scheme estimating the non-time dependent components of the model. And what I'm showing you here is up here, basically the plot I showed you earlier, when you are trying to model temperature without a time-dependent component. And when we introduced the time-dependent component, you could see how much better we were able to capture some of these departures and more closely adhere to the basic assumptions, likelihood assumptions of Bayesian inference. You can also see that the uncertainty as a result is somewhat broader, meaning that perhaps this was underestimating the uncertainty. Again, not atypical of that kind of overconfidence is not atypical of when you have incorrect statistical assumptions. Again, thinking about maybe the selection. So here's what we could reconstruct as a kind of result of the model. This is the pattern of historical deviations that we might see. And while we weren't able to necessarily associate this pattern with anything known, any known shortcomings of the model, conceptually at least, I think this is an advance because one could look at this and say, all right, what could have this time-dependent component to it? And then perhaps that would be then an element that we would need to add to the model to make it more realistic, rather than adding, trying to increase the realism of a model kind of willy-nilly, doing it in such a way that we actually would lead to improvements in the key ways that we find statistically. And again, then we have distributions, Bayesian posterior distributions, the solid lines here, that are reliable because they are coming from reasonable likelihood functions. The other key component of Bayesian analysis is the prior. And that's also something that's uncertain. I tended to kind of do some hand-waving before and say that comes from subjective assessments and anyone can have their own. Well, in reality, if we're going to have a climate model that we're going to base policy decisions on, we can't necessarily have everybody coming up with their own assessments. And yet there is a lot of disagreement. Again, one of the key parameters is this climate sensitivity parameter. And there's particular uncertainty and disagreement about this, as I mentioned earlier. Just to remind you, climate sensitivity is defined as the equilibrium global temperature response to a doubling in radiative forcing. And while the climate scientific community has taken to trying to assess distributions to these rather than assuming that they're fixed values, you can see different studies have led to wildly different distributions for that key model parameter. And it's not just a key parameter in our model, it's actually key in just about any climate model. One way or the other has to capture this basic element. So how do we deal with this? How can we, if any one of these, how could we use any of these as a prior? Well, conventional Bayesian inference assumes that probabilities are unambiguous, that we can have a probability distribution that represents uncertainty, but there's no ambiguity above and beyond that. In reality, as I just showed you, the exact shape and spread of the probability distributions is typically unknown or is subject to substantial disagreement. And this ambiguity, I think, is important to remember, is distinct from the uncertainty that's embedded in the probability distributions themselves. It's a kind of second order uncertainty. All the scientists admit that there's uncertainty and are willing to come up with a distribution, but they all choose different distributions perhaps because of their different past experience or different expectations. So we need some kind of methods that can describe, quantify, and then form the kind of probabilistic reasoning under this type of uncertainty. And it's not something that has typically been done in the past. What we're after is a way of replacing single probability distributions with sets of distributions in which all members of those, we can come up with a definition whereby then all members of that set might be considered to be feasible. Well, it turns out in the statistical literature, there's a lot of different ways out there to define sets of distributions. They have different names, they go by different basic principles. There's the density ratio class, which defines it as in terms of a ratio of two different density functions. There's a quantile class. There's something called an epsilon contaminated class, something called p-boxes. What we found to be the most conceptually compelling is the density ratio class. The density ratio class allows basically any density function to be considered allowable if it can be drawn between two unnormalized upper and lower density bounds. So in other words, if we were to draw curves that might otherwise represent probability densities, the area between those curves, anything we could draw that would fit between those would be allowable according to this definition. And I say unnormalized because the upper one, obviously these can't both be normalized in the sense of integrating to one, because then they wouldn't allow anything in between them. So we have to draw things that look like density functions in terms of shapes, but one of which isn't normalized. And so this is conceptually nice because it has an easy interpretation. It's basically saying it's the set of all density functions for which that once we normalize it, it basically falls between this lower curve and this upper curve. So it's easily defined. It also turns out to have some other important advantages. It's been proven that the density ratio class is invariant under Bayesian inference and marginalization. What that means is that if you were to start out with a Bayesian prior using this model construct, this density ratio class, and perform Bayesian inference, you would end up with a posterior that could also be described by a density ratio class. And that's not so obvious, and it's not the characteristic of many of these other definitions. In pursuing this particular formulation, we also ended up proving that the density ratio class is invariant under propagation through deterministic models. Meaning if you take a probability distribution of an input or parameter, use it as the basis for developing forecasts, then the output itself of that model could also be described by a density ratio class. And it turns out that the outputs of stochastic model, outputs of models that come from stochastic model, outputs of stochastic models in which the inputs are defined by a density ratio class are also themselves embedded within a density ratio class. Not necessarily the smallest possible density ratio class, but you can construct a density ratio class that contains all the sets of output. And so these were important because basically what these invariance properties do is they allow you to work within one consistent mathematical framework under a sequential process of learning and updating and forecasting. Just like you could do with precise Bayesian distributions, but now having this additional level of potential ambiguity. So we turned back to the climate situation, and we defined a density ratio class that was fairly broad in containing all the previous estimates, all the previous distributions of climate sensitivity. So we basically chose a lower density that undergirded any of the, or I should say maybe lied underneath any of the other distributions for climate sensitivity that were out there, and an upper limit, which we essentially chose to be flat, that would allow anything else, any of these to be drawn within these. So it's very tolerant set. And we were interested to know whether, given the information after we had developed that previous model and made the correction in the likelihood that we did, whether we could pin down the value of climate sensitivity using the available data, even if we use this very broad range of priors. And it turns out more or less we could. The posterior looks like this, meaning we can pretty well define the distribution of climate sensitivity, except for, again, this upper tail may actually be quite thicker than we would otherwise expect. In other words, there's a greater chance than a typical distribution would show of more extreme outcomes. And in the process of doing this, we developed and published some numerical algorithms for implementing this that basically minimize the computational burden relative to more conventional approaches, which we felt like was important. If we're going to introduce a new concept, it couldn't be overly complex. Now, what's important is now we can use these density ratio class sets to produce predictions for the variety of greenhouse gas mitigation scenarios that are being considered. So here are just different future forcing functions that IPCC has used for some of its assessments, and then these projected distributions of output in the form of say, global average temperature. Again, as we proved, follow a density ratio class, and it turns out that these are the density ratio classes for at least 4 of these particular scenarios. And you look at these and you say, all right, well, maybe there's not that much difference in the shapes between the upper and lower bounds, but it has a very important interpretation here. For example, if we have a key threshold that we don't want to exceed, like 2 degrees, for example, now rather than having probabilities, we have lower and upper bound probabilities on those exceedances. And these lower and upper bound probabilities are intended to capture both the state of the current predictions, but also the potential for improvement, right? Where could we gain more information in order to reduce this ambiguity and have more precise measurements of some of these key components on which we would be basing decisions. When we finally now go back and connect this with economic assessments and the utility function, rather than having a single curve that kind of shows the utility as a function of emissions reduction, what we now have is an envelope where this range results from the ambiguity contained in these imprecise probabilities, or the density ratio class. And the expected utility criterion that I argued for earlier no longer holds. There's no longer a unique maximal expected utility, because we're saying anything within the shaded area is considered to be feasible. So we need some kind of secondary criterion. One alternative might be maximal lower expected utility. That is, we choose the highest value on the lower envelope. You could think of this as being consistent with the precautionary principle, or kind of maxi-min principle. It says that we want to choose the value, the decision, that has the highest possibility of the worst possible outcome. Right? It's very precautionary. It's say we're going to concern ourselves with the worst possible situation, the lower envelope of utilities, and pick a level at which that worst possible level is the highest. And so that might be a criterion one could use under this circumstance. So we're not entirely paralyzed with this level of ambiguity, but it gives us a need to think more broadly about what our decision criterion is in such a case. Okay, so wrapping up this component here, I want you to come away with a message here that in the case of risk, in the case of climate change, like so many risky events, there's generally a much higher probability of unexpected or even catastrophic impacts than we might otherwise think. And I'm not the first to suggest this. It's been part of the kind of notion of black swans or fat-tailed distributions for a long time. But certainly we've demonstrated this in the context of climate change from a number of different fronts. The key component is since society is generally risk averse, as we see every day in insurance, say, purchases, but also what we see in basic activity in the stock market, the risk premium, again, being described by social risk aversion. When we introduce that level of risk aversion, then the risk reduction value of emissions abatement becomes enormous. Allowing for time dependency in the parameters of any model, say a climate model, enhances the model's flexibility and supports model development in the future. And so a formal process whereby we can anticipate learning from new observations and new evidence and update the uncertainties associated with our model with that new evidence is an important and reasonable way to proceed in a dynamic environment like we face today. And then finally, using ambiguity, representing ambiguity, which might be a very different thing from natural variability or uncertainty or risk, can be represented by these kind of mathematically tractable imprecise probabilities, as I demonstrated. So what does this mean more holistically? I want to tie this back a little bit to the concept of resilience, which I introduced the talk with. I want to remind you what I mentioned. Resilience essentially is a requirement that we have continued performance in unexpected situations. And this typically requires dynamic assimilation of new information and adaptation to change. And so Bayesian decision theory as a whole supports this by promoting decision-making under uncertainty in a rational way and adaptive management, that is learning by doing. And in particular, some of the more sophisticated approaches that are being developed, like hierarchical Bayesian methods, are useful in data-poor situations, which often are the case in which situations have no historical precedent. And robust Bayesian analysis can handle ambiguity that's similarly prevalent in new and unprecedented situations. And importantly, it supports identification of robust or resilient decision strategies, ones that can do reasonably well even under the worst of conditions. So I think these kinds of numerical frameworks are important ones to use as we explore topics of resilience. What are some of the next steps that we're going to take as a research group? Well, one of the things that we're actively working on, or we've been looking into and we're more actively working on moving forward, are other elements of decision-making under uncertainty. Another really important concept is game theory. And I think game theory is especially relevant in today's world in which many problems are framed as either zero-sum situations or as adversarial kinds of conditions. Climate change negotiation being one of them. And so we want to further explore game theoretic aspects of negotiating a climate treaty under uncertainty. One way of thinking about this is climate negotiators actually aren't only negotiating with each other, they actually have to achieve an agreement that's successful once they come back to their home country. It has to be something that the domestic constituents, whether it be Parliament or Congress, have to be able to ratify or agree to, and the domestic economy has to be able to operate under. And so with that framework, what we're trying to explore is what kinds of specific negotiation structures or treaty types might be able to be more robust or more resilient when we have unexpected events at each of these levels. That is, when perhaps oppositional countries who sign on to that treaty may or may not necessarily follow through on their agreement. We could have global events of an economic nature or any other nature that might disrupt our ability to meet those targets. Or simply domestic issues, like, again, maybe economic disruptions or changes that might be of a positive nature, say a new invention that allows us to achieve lower carbon intensity. How do the treaties that are developed under such situations, how can modeling, quantitative modeling of the kind that we're talking about, support treaty types under those situations that can be robust to those unexpected outcomes? So I want to acknowledge people that have contributed to this work. The work that I described specifically today was in collaboration with these faculty colleagues at Dartmouth and elsewhere, and was funded by a combination of grants from EPA and from the National Science Foundation. These are just some other people that have been in my group over the last few years that have earned their PhD or their master's or worked with me as a postdoc. And I have two group members here that you'll see here in the audience, Kimberly and Varun, and you'll see around Pratt that have joined me, or in the case of Varun, moved with me from Dartmouth, and Kimberly joined since I arrived. And then I've had a number of undergraduates work with me then over the years as well on these projects and other related ones. I don't want to keep you very late, but I'm going to, as I take questions, I thought I'd put this slide up, which just describes in just a brief phrase some of the other projects that I've been involved in recently or continuing to lead. Projects that range from management of land under disturbances, things related to economic assessments of water quality and small stream benefits, and then other aspects of disturbances and trade-offs, both with respect to human health and the environment. I'd be happy if any of you have interest in these to direct you towards papers or have a discussion. So, thanks for your time.